Hello. Hello.
Yes, sir.
So can you see the screen, this whiteboard screen?
Yes, sir.
Okay. So this I have already done in the last, but if you want, then I can do it again on the another whiteboard. Or should I do it on the previous? Uh, Anyway, I have written this in the last tutorial class, isn't it?
Sir, the first question had a lot of details, so if you could explain the diagram
Yes,
by
yes,
making
yes,
it
yes,
again.
yes. I'm doing that. Okay. So what is been given here is a 6 meter cube polymerization reactor has an outer jacket for heating or cooling as necessary. In a particular batch, 5 meter cube of monomer at 24 degrees Celsius is charged into the reactor. The charge has to be heated to maybe I will do it on the next this, then probably you will appreciate it more. Okay, just wait. Okay. Let me do it on the another whiteboard, then probably you will Anyway, I have done it in the last tutorial, but then when we write it, then the understanding is more, isn't it? So probably I'll do it again. Just wait. Okay. So the question is, there is a 6 meter cube polymerization reactor which has an outer jacket for heating or cooling as necessary. In a particular batch, 5 meter cube of monomer at 24 degrees Celsius is charged into the reactor. The charge has to be heated to 80 degrees Celsius before the initiator is added to start the reaction. The liquid in the reactor is well stirred, and the liquid side heat transfer coefficient is 400 watt per meter square degree Celsius. Hot oil flows through the jacket at a sufficiently high rate, and the average oil temperature is 125 degrees Celsius. The oil side heat transfer coefficient is 300 watt per meter square degree Celsius. If the available heat transfer area is 10 meter square, calculate the overall heat transfer coefficient and the time required for heating the charge to the desired temperature. The relevant properties of the monomer are density equals to 870 kg per meter cube. Specific heat is 1.81 kilojoule per kg degree Celsius. Thermal conductivity is 0.25 watt per meter degree Celsius. Estimate the liquid film thickness on the monomer side. What would be the heat transfer coefficient for water corresponding to this liquid film thickness? Neglect the thermal resistance of the wall. Okay, so what is been given is you have been given a reactor. So maybe reactor is something like this. There is a reactor. Okay. There is a reactor like this, isn't it? So monomer is there. Okay. And outside this reactor, there is a jacket. Outside this reactor, there is a jacket. Okay. Okay. Now, what is been given is the volume of this reactor is given, that is 6 meter cube is given. Okay. And inside this reactor, there is a 5 meter cube of the monomer is there at 24 degrees Celsius initially. So T1 initially the monomer is at 24 degrees Celsius. Okay. This monomer has to be heated to a final temperature of 80 degrees Celsius. That is what is been given in the problem, isn't it? 80 degrees Celsius. Correct. 80 degrees Celsius. This is what the final temperature is. Now, how this monomer is heated inside the reactor? By a oil, hot oil, which is flowing through this jacket and which is coming out from here. The temperature of the oil is given as 125. 125 degrees Celsius. This is the temperature of the oil is given. Okay. Again, what is been given is the heat transfer coefficient HI is given. So HI here inside the monomer liquid side, that is given as 400 watt per meter square degree Celsius, and the outside heat transfer coefficient here is H naught, which is given as the oil side heat transfer coefficient is given as 300 watt per meter degree Celsius. Okay, correct. Now what we have to find out is, in this particular problem, what we are interested in finding out is how much time will be requiring for increasing the temperature of this monomer mass from 24 degrees Celsius to 80 degrees Celsius. Correct. That is what we are interested in. Now, since the volume of the reactor is 6 meter cube, isn't it? 6 meter cube is the volume of the reactor. The following assumptions we can make here. Assumptions which we can use here are assumptions. The first assumption is the the thickness of the reactor vessel is assumed to be small compared to the diameter or radius, whatever you can say, isn't it? So what we are doing it here is basically the thickness of this metal wall we are assuming negligible compared to the radius. So what information it gives is basically with this assumption what we are going to have is Ri, which is the inside radius here at the metal wall, and R naught, both are same. This is the realistic assumption because the volume of the reactor is 6 meter cube, isn't it? So compared to that, definitely the reactor thickness will be very small, isn't it? So compared to the reactor diameter or a radius, the thickness of the reactor wall is going to be very small. So this is a realistic assumption. Then the second assumption is which we can.
Hello, sir.
Yes, please go ahead.
So when we say that Rf is equal to R naught, aren't we saying that the thickness of jacket is negligible?
Yes, that is what we are saying, because see there is a in outer jacket. No, we are not saying jacket. Outer jacket is where the oil is flowing. Inside the reactor there is a monomer in the liquid state, and both are separated by a reactor wall which is made up of metal. Now you are able to get it.
Sir, can you please mark R naught in the figure?
So this is going to be Ri, and this outside here is going to be R naught. So this is the metal wall.
All right, sir.
Are you able to get it? And this is the jacket. This is, maybe I just show it by a different color. So this is the jacket. This is the jacket from in which there is a oil is flowing, isn't it? So oil is flowing here. Oil. Correct? So this is oil out. Again, what is been given is the flow rate of the oil is sufficiently high. So because of that, even though there is a heat transfer is taking place, but the temperature T naught is going to remain same as 125, isn't it? That is what is been given in the problem statement itself. Again, oil and monomer is separated by a metal wall, isn't it? So reactor is made up of metal, isn't it? So metal wall, correct? So it is separated by a metal wall, correct? So clearly what it means is the resistance offered by a metal wall we can neglect safely, isn't it? So the resistance offered by metal wall can be neglected. Is it clear to everyone why these two assumptions are used? Isn't it? That is why the radius and outer radius as well as inner radius of the reactor is not been given, isn't it? You can calculate that anyway. You can calculate the inner radius if you wanted to, because the volume of the reactor is given, isn't it? And you can assume the but length is not given, isn't it? So again you will not be able to calculate. So Ri equals to R naught. This is the reasonable assumption. Again, this is kind of a cylindrical structure, isn't it? Okay, cylindrical system. So now with these assumptions, what we can write down here is, remember here what is happening is the heat transfer is taking place in a oil side, the heat transfer is taking place in a monomer side, and the heat transfer is taking place through this metal wall. So there is a heat transfer taking place here somewhere, isn't it? Then the heat transfer is taking place inside here in the reactor, and the heat transfer is also taking place through this metal wall. But the heat transfer resistance through this metal wall we have neglected, isn't it? Correct. So in this case, the overall heat transfer coefficient Ui we can write in terms of the inner radius, that can be written as 1 by Hi plus Ri by R naught 1 upon H naught, isn't it? Are you able to understand why I am writing this? Isn't it? I am writing the heat transfer coefficient in terms of the overall heat transfer coefficient because there is a heat transfer taking place in a oil side, there is a heat transfer taking place in a monomer side, and also there is a heat transfer taking place through the metal wall. But the resistance, heat transfer resistance offered by the metal wall we are neglecting, so that in between term is cancelled out here, isn't it? That anyway I have got rid of. So I am left with only two terms. The first one is, this is the heat transfer coefficient corresponding to the liquid side. This is the heat transfer corresponding to the oil side, isn't it? And since this Ui is defined in terms of the inside surface area, I will have Ai divided by A naught. So Ai divided by A naught will be, in this case, uh, basically Ri by R naught, isn't it? Pi dl is going to be the area for the cylindrical system, isn't it?
Hello, sir.
Yes, please go ahead.
Sir, it should be 1 upon Hi, I think. So we did this in the lecture.
That's right. What you are trying to say?
Sir, 1 upon Ui is equal to 1 upon Hi plus the rest of the terms.
No. This equation is correct. This equation is correct. Let me just check if I have made the mistake in the class lecture notes. Just wait. I think I made the mistake in the class note. This equation is correct. That is that 1 by Ui, instead of that 1 by Ui or 1 by U naught, that should be just Ui or U naught. There. Okay. I will correct it in my class notes slides. So yes, I have made the mistake in the class notes slide, so that has to be corrected. I'm sorry. That has to be, instead of 1 by Ui or 1 by U naught, that is just U naught and Ui. That's it. That 1 by term is not there. In fact, I have already corrected in the slides. Thank you. Thank you for pointing. That is just the copy paste from the above equation, so that 1 by factor is coming in. Anyway, I have corrected in the slides. Okay.
All right, sir.
So maybe I can project it also. If you need, I have already corrected in the slides. So this is what you are saying, isn't it? Can you see? Can you see the equation?
Yes, sir, I can.
So this I have corrected already. Thank you. Thank you for pointing. Yes. So equation which I have written here in the whiteboard is correct. Okay. Let me just open it. Okay, so now here all the values we know, so we can directly find out the overall heat transfer coefficient, isn't it? So overall heat transfer coefficient again, see in this case Ri is same as R naught, so doesn't matter whether we put it this subscript or not, it is still going to be the same. So we can directly write down this as 1 by U is given as 1 by Hi plus 1 by H naught. So we can put the values here. So 1 by Hi is 400. 1 by 300. So this comes out to be this is going to give me U, and U value of U comes out to be 171.4 watt per meter square degree Celsius. Okay, are you all getting the same? Isn't it? Is it correct?
Yes, sir, it is correct.
So now make the heat balance. So heat balance in this case will be what? Remember what is happening here is the heat is getting transferred from the oil to the monomer, isn't it? So whatever the heat is getting transferred from the oil to the monomer is going to increase the internal energy of the monomer, isn't it? So rate of increase in the internal energy will be same as the amount of heat that is being transferred from the oil to the monomer, isn't it? So we can write down that in terms of the heat balance. So heat balance in this case is going to be mCp dt by dt. So that is nothing but how much is the internal energy increasing in the monomer side, and that should be given as the amount of heat transfer from oil to the monomer. So that can be given by a Newton's law of cooling. So that I can write down as UA T naught. T naught is nothing but the temperature of the oil minus T, where T is the temperature of the monomer mass inside the reactor. Correct? Is it correct?
Yes, sir.
So now the boundary conditions here are so boundary conditions here are at T equals to 0, T equals to capital T equals to T1, so that is equals to 24 degrees Celsius, isn't it? And at T equals to Tf, that is the final time which we wanted to find out. So T equals to T2, and that is 80 degrees Celsius, isn't it? We can integrate equation number 1. Integrating equation number 1, what we get here is sorry, this should be I think 2. Okay, I'll just correct it. So what you are expected to get is this. Check whether this equation is correct or not. So after integrating equation number 1, this is what you are expected to get. Is it correct?
Yes, sir.
So you can put the values here. So you can put the values 125 minus 20 minus 80 divided by 125 minus 24, and that should be equals to exponential of minus U. You have already calculated, so that is 171.4. Area is already given in the problem statement itself, isn't it? So A is given is 10 meter square. If you read the problem statement, the area of the heat transfer is given, so that is 10, isn't it? Mass of the monomer you can calculate, because the volume of the monomer is given. So volume of the monomer is given. So volume of the monomer multiplied by the density, that will be giving you the mass. So here 5 meter cube is the volume given, and the density is 870. That is the monomer density, and multiplied by Cp. So Cp here is 1810 into Tf. So you can calculate from this the Tf. Calculate the value of Tf, that is the time required for increasing the temperature of monomer from 24 degrees Celsius to 80 degrees Celsius. Is it correct what we are doing?
Yes, sir.
So Tf comes out to be, anybody? Check whether this is correct.
Yes, sir.
Okay. So
Yes, sir,
are you all able to understand what we have done here? Okay. So now the second part, this is the first part. Second part of the question, what is the second part? We have to calculate the liquid side thickness, liquid side film thickness, isn't it? So remember what is the expression HI? If you calculate the HI is nothing but what? The thermal conductivity of the liquid side divided by the film thickness of the liquid side, isn't it? So we have to calculate liquid side film thickness. So that will be given as KL divided by HI. So thermal conductivity of the monomer is already given, that is 0.25 divided by HI is also is given, that is 400. So this comes out to be 0.000625 meter, isn't it? So that is 0.625 mm. Okay. This is what the film thickness is, isn't it? So liquid side film thickness is 0.625 mm. Now what is been asked in the question is, instead of monomer, suppose the liquid which is inside the reactor is replaced by, let's say, water. Then for the same film thickness what we have obtained right now, what will be the heat transfer coefficient? That is the question. Okay, so this film thickness is common. So delta L equals to 0.000625. This is common. But now instead of monomer we are having the water. So this will be given as Kw by Hw, where Kw is the thermal conductivity of the water, whereas the HW is going to be the heat transfer coefficient if the water is used instead of monomer. So the thermal conductivity of the water is known, isn't it? Water I have already given in the first the conduction lecture slide. If you see there, the thermal conductivity of the water is given, that is 0.65. Even if you are not able to remember that, all these values are given in the backside of your book. Backside of the book, all the values of water, at least for water and air, are given. So Kw is 0.65 watt per meter degree Celsius divided by HW. We can calculate what will be the transfer coefficient if the monomer is replaced by the water. So that can be given as 0.65 divided by 0.000625. So HW comes out to be 1040, if I'm not wrong, watt per meter square degree Celsius. Check whether this is correct.
Yes, sir.
Yes, sir.
Correct. So this is the second part of the question. Okay. So here I'll just write down Kw is given as 0.65 watt per meter degree Celsius. Okay. So these are both the parts of problem 1. Let us look at the problem 2. Now let me just copy the description of this question. Okay.
Sir.
Now what is been given in this question is the steady state radial temperature profile in a 10 centimeter diameter sphere is known to be. So I am writing this here. The square is not visible correctly. So this is 10 raised to the power 3 here. It's not 103. OK, so I'm just writing down the correct expression here. So what is been given is the temperature distribution along the radius is given for a 10 centimeter diameter sphere. OK, so T is given as 101.39 minus 1.389 into 10 raised to the power 3 R square. This is the correct expression. OK, and T in degrees Celsius and R in meter. OK, this is what is been given. So here the radius is also given. So radius are not, maybe I will write down that as capital R. Capital R is given as 0.05, isn't it, in meter? Correct. And thermal conductivity is given. Thermal conductivity 12 watt per meter degree Celsius. This is what is been given. Ambient temperature is also given. So TA is 30 degrees Celsius. OK. Now, what is been asked in this particular question is, do you think what is the maximum temperature in the sphere? That is the first part, isn't it? What is the maximum temperature in the sphere? So part A, T max is what? That is what is been asked. Now, if you look at the temperature profile, let's say this is equation number 1. If you look at the temperature distribution here, so clearly here the temperature decreases as the radius is increasing, isn't it? Because 1.389 into 10 raised to the power 3 into R square, there is a minus sign just before this, isn't it? So as radius increases, the temperature is going to decrease, isn't it? So clearly my maximum temperature is going to be at the center when radius R is equals to 0, isn't it? So T equals to T max when R is 0, isn't it? So we can put this in the equation from equation 1. From 1 we can get T max is 101.39 degrees Celsius, isn't it? So this is going to be the maximum temperature. Now what is being asked in the second part is, do you think that there is a heat generation in the sphere? Isn't it? So in this particular problem, you can clearly see there is no heat coming in, but there is a constant dissipation of the heat is taking place, because that is the reason why the temperature inside at the center is maximum and the temperature is decreasing as you are moving along the radial direction, isn't it? Correct. So the temperature at the center is maximum and it decreases as you move along the R. Decreases with increase in R. Correct. So since there is no heat input in this particular sphere, at least it is not given in the problem. So clearly there must be a heat generation source. Since no heat is coming in, there has to be heat generation inside the sphere. Okay, so clearly we can conclude that there should be a heat generation inside the sphere. Correct.
So,
yes, please go ahead.
So I didn't understand this logic.
Okay. Suppose there is a heat coming in from the outside. There is a heat coming in from the outside. Do you think we will have a temperature at the center maximum? Suppose no, there is no heat generation at all and the heat is coming in from the outside. So how the temperature is going to vary inside the sphere? It will be maximum at the surface and it will be minimum at the center, isn't it?
So what if the sphere was already warm when we started studying it and it was warm from inside?
What you are saying is sphere is
Like when we are studying the sphere, it was already hot from the inside, and the mechanism of how it was heated from the inside first is unknown to us.
yes, but we are not looking at the unsteady state here, isn't it? That is the unsteady state case.
Yes, all right.
Isn't it? That's an unsteady state case. We are not looking at unsteady state. Here we are saying that it's a steady state, and at the steady state, the temperature profile is given is for the steady state, isn't it? So clearly that steady state profile you can have only if there is a continuous heat generation.
Yes, sir.
Okay. Okay. Now what is been asked in the question is, if I go up and just look at the question, do you think there is a heat generation in the sphere? Yes, there will be heat generation in the sphere because look at the question. In the question it is given clearly it's a steady state, isn't it? Steady state radial temperature profile, isn't it? Clear? So again, so answer is affirmative. There will be a heat generation inside the sphere. If so, at what rate? Now we have to find out the rate at which the heat generation is taking place. So what we are interested in? We are interested in finding out psi, which is nothing but volumetric rate of heat generation. Correct. So now, since in this case there is no heat coming in, there is only a heat dissipation taking place from the outer surface, isn't it? So the total amount of heat dissipated from the outer surface we can directly obtain as, so Q is nothing but the heat dissipated from the outer surface of the sphere. So that can be directly obtained as, pi 4 pi r square, maybe I just put it outer surface, so there will be a capital R, 4 pi r square minus k dt by dr at r equals to r. So this is going to give me the total amount of heat dissipated from the surface, isn't it? Heat dissipated from outer surface, isn't it? Correct. So this is the total amount of heat that is getting dissipated from the rate of heat dissipation from the outer surface, isn't it? This is the rate of heat dissipation from the outer surface. Correct. So here the radius we know, thermal conductivity of the sphere we know, dt by dr we can directly obtain from the equation number 1, isn't it? So from equation number 1, dt by dr that can be obtained as 2.778 into 10 raised to the power 3 r, isn't it? And dt by dr at r equals to r, that is 0.05, you can put it that value here, 2.778 into 10 raised to the power 3 into 0.05. So that comes out to be 138.9 degrees Celsius per meter, isn't it? So now we can put this in this particular equation. So Q can be obtained as 0.05 square. Thermal conductivity is already given, so that is 12. This negative sign is here, so this negative sign get cancelled out with this negative sign. So multiplied by just 138.9. So what you get is Q comes out to be 52.36 watt. Is it correct?
Yes, sir.
Now this amount of heat that is getting dissipated is nothing but the amount of heat generated by the internal heat generation, isn't it? Whatever the heat that is continuously, whatever the rate of heat dissipation should be same as the rate of heat generation, isn't it? Then and then only at steady state we will have a continuous dissipation with this rate, isn't it? Isn't it? So clearly this Q, which is 52.36, should be same as volume of the sphere into psi v, because psi v is the volumetric rate of heat generation multiplied by volume. So that becomes 4 by 3 pi r cube into psi v, isn't it? So I can put all the values here. So 52.36 should be equals to 4 by 3 into 3.14 into 0.05 cube into psi v. So I can calculate psi v from this. Psi v comes out to be around 100 into 10 raised to power 3 watt per meter cube. Just check whether this is correct.
Yes, sir, it is.
Does it make sense? So what we have equating here is the rate of heat dissipation should be same as the amount of heat, that is the rate of heat generation inside the sphere, isn't it? Then and then only we will have a steady state, isn't it? So continuously we will have a same temperature profile, isn't it? Whatever is governed by equation number 1. So is it clear to everyone what we are doing?
Hello, sir.
Yes, please go ahead.
Sir, this psi v is a constant or a function of R?
See, when we started with that derivation, we have used psi v as a function of R, but then we have obtained the final expression with the simplification saying that the psi v is uniform throughout and is constant. It is not varying with R, or it is not varying with X.
No,
So
sir.
psi v is the volumetric rate of heat generation which is constant throughout.
Sir, for this temperature profile, I do a back calculation and found that if we apply cell balance, then we get Q as a function of SC by R. Matlab, R to the power -1 dependence. But from this temperature profile, this is R dependence. So why this is ambiguity?
Okay, so what you are trying to say, see, you are saying that the temperature profile you have obtained, yes, then?
Sir, if we apply a cell balance to a normal sphere, then we get dt by dr. Dt by dr is equal to minus k dt by dr is equal to SC by R. So there is R is in denominator. And for this temperature profile, when we calculated dt by dr, it is R multiplied in numerator. It is directly proportional to the R, and from the cell balance we got inversely proportional to the R. So I might be thinking that this SC is not constant in this particular question.
SC or psi you are saying?
Yeah, psi, sorry.
So you are saying the psi v is not constant in this case. That is what you are trying to say?
Yes, sir. Yes, sir. This psi is calculated at the R, and it might not be the case that it is constant for whole sphere.
Okay, so this psi v you are saying will be exactly at R equals to R.
Yes,
R equals to capital R, but for other it might not be a constant value, isn't it? That is what you are trying to say?
Yes, sir.
That I have to check. Whatever you are saying, I am not refuting. Yes, this indeed the question every year people say. I perfectly agree with you. Probably this is the function of R. That is why you are getting that specific expression for the temperature profile, isn't it?
Yes, sir. Yes, sir.
But this psi v is at R equals to small r equals to capital R. That is what you are trying to say?
Yes, sir.
Okay, so then probably yes, I will back calculate everything, and we can discuss probably in the next tutorial class, but I am not refuting your analysis what you have done.
Okay,
it could
sir.
be a function of R, yes, because otherwise there will be ambiguity with respect to the temperature profile which we have started with. That is what you are trying to say?
Yes, sir.
Sir,
Okay.
I think that it will be different for different R because it is
Yes, yes,
heat
yes.
generation per unit
Yes,
volume.
yes.
So the heat should be
I'm not saying
same.
no. I'm not saying no. I'm saying I agree with you. I am saying yes. I'm not saying no.
Sir, I did it by another method, and what I did was to see whether heat generation is taking place or not. I used the general expression where there is a source of heat inside a sphere, and sir, I just compared it with the temperature profile given. So it showed that yes, the heat generation is taking place one, and the expression I had got, it was something like a constant multiplied with r square. So it told me that the 5 is actually the constant. So what I'm trying to say is that 5e for me is coming constant for all r, I think. Because I use the general equation. Sir, I can share my screen to show you
So you
maybe.
have solved that problem in the class actually, and it is a function of R. Exactly, the temperature profile is similar to what you have given in this question.
That's what I'm saying. See, generally what happens is for the initial balance, we solve by assuming that psi v is a function of r. But thereafter, all the simplification we do by assuming that psi v is independent of r, isn't it? So that we do. But here I have to check what you are saying is both cases. One is saying will be a function of r, and the another one is saying that the psi v is constant. Let me check it carefully. Okay. So now let's move to the uh, last part. Now what is the last part? The last part is we have to calculate the film coefficient, isn't it? So film coefficient we have to calculate uh, for the given case, isn't it? So there is a heat dissipation taking place from the outer surface of the sphere, isn't it? So there will be a film of the air outside the sphere, and we have to calculate the heat transfer coefficient for this the film outside the sphere. Okay, so that can be given as in part C. In part C, what is being asked is heat transfer coefficient H we have to calculate, isn't it? So Q, which is nothing but the heat dissipated outside, should be same as which we have already calculated, should be same as HA delta T, isn't it? So here H we have to calculate. Area we can calculate for the sphere, isn't it? So area for the sphere we can directly calculate as 4 pi into 0.05 square. Okay. Into delta T. Delta T in this case will be what? Delta T in this case is going to be T at the surface of the sphere minus T ambient, isn't it? Now the temperature at the surface we can directly obtain. Temperature at the surface we can directly obtain. Ts can be directly obtained from the expression 1. So that is given as 101.39 minus 1.389 into 10 raised to power 3 r square, and this has to be calculated as r equals to r 0.5. So if I put it, Ts comes out to be 97.9 degrees Celsius, and if you put it in the equation, what we get is 52.36 is given as H into 4 into 3.14 into 0.05 square into Ts is 97.9 minus ambient temperature was given in this particular problem. Ambient temperature was 30 degrees Celsius, isn't it? So we can back calculate H, calculate the value of H. Is it clear what we are doing? Hello? Hello?
Yes, sir, it's clear.
So how much is the value of H? 24 point something?
Sir, it's coming out to be 24.54.
Okay. Now let us go back to the same question which we were looking at. This question is completed. Now let us look at the query which we had. Okay. What was the query here? Hello. The query here was this psi v will be a function of r. That is what some students were saying, and some students were saying that psi v will be a constant, isn't it? Hello.
Yes, sir.
Okay. So okay. Now those who got this psi v as a function of, why you are saying that it will be a function of r? Anybody? Just let us discuss this. Probably we can complete it in today's class. Hello.
Yes, if we apply shell balance to this spherical
Okay. Shell
ball,
balance to the spherical thing. I'll just open it. Maybe that will give us a better discussion. Okay. Just wait. Let me just open the shell balance for the spherical case. So in the spherical case, what you get is probably minus d by dr r square qr equals to r square qr plus r square psi v. That is what you get, isn't it? If I am not wrong, I'm just trying to open that. Just wait. Okay. So shell balance you are saying for the spherical case. Okay, so I am just projecting it. Just wait. So this is what the equation we have got, isn't it? Minus d by dr r square qr plus psi square r square psi v equals to 0, isn't it?
Yes, sir.
Okay, then after that, what you are trying to say? Hello?
sir, if we find k dt by dr from this equation, then we get 1 by r dependence.
From this equation which we have looked at, isn't it?
Yes, sir.
Okay.
Equation number 32. Next slide, please.
Just wait. Just wait. Just wait. So next slide you are saying if we so in the next slide we have again integrated it, isn't it? But then we have assumed that this psi v is independent of r. Hello?
Sir, sorry, sir, sorry, sir. I got my calculation mistake.
And so that will be psi v will be independent of r.
Yes, sir. Yes, sir. I got it.
Okay. Because otherwise in the differential, if this psi v will be a function of r, we have to account that functionality also in the integration.
Yes, sir.
Okay. Since we are assuming that this psi v is constant, we can take it out easily, and then with respect to r square, the different integration is performed. That is why this is coming, r cube by 3 plus c1. So I think this psi v is constant, isn't it? That question was there, isn't it? Is it clear to everyone?
But sir, if a psi v is multiplied by volume, this is constant. So we know that volume is changing from 0 to r. So
Okay.
this implies that psi v should also change from 0 to r so that the overall q is constant.
No. What you are trying to say? Please come again. Yes. You are saying that the volume is changing. That's why psi v should also change. See, the total, that is why the total amount of heat dissipated we are calculating at R equals to capital R. We are not calculating in between, isn't it? In between only there is a accumulation term is taking place. All whatever the heat generation. See,
Sir,
if there is
that
no
Q will be also same inside as well everywhere because this
small
is a
q
steady
is going
state.
to vary. Small q is going to vary.
Yeah, I'm talking about capital Q, which is constant. We have taken capital Q, I think.
Yes, yes, yes. So then what you are trying to say?
Sir, you have equated capital Q is equal to volume into psi v.
Yes.
So if volume is changing, for example, this Q is valid at R is equal to capital R by 2, half of the radius.
Okay.
So at that point, the
So
volume
that
will be
I
different.
have done it at R equals to R because this 52.36 which I have calculated, that I have calculated outside, isn't it? Because the dissipation is taking place outside. Remember, this Q is nothing but the rate of heat dissipation, which I have equated to the rate of heat generation that is entire in the entire solid. I am not looking at only one small part of the sphere. See, inside the entire solid sphere, there is a generation which is taking place, isn't it? So that total generation I have equated to the amount of heat that is getting dissipated outside. So that is why I have calculated capital Q at R small r equals to capital R, because the dissipation is taking place only at outside. Inside there is no dissipation, isn't it? So what you are trying to say is this capital Q, you are saying that this capital Q I have calculated only at the boundary of the sphere. I have not calculated inside. Basically, this capital Q is going to vary inside. If you are trying to look at what will be the Q at a specific radius, that is going to vary, but psi v is going to remain constant. Psi v is going to remain constant everywhere. Is it clear?
Yes, sir.
Psi v is going to remain constant because that is the volumetric rate of heat generation. So if you reduce the volume by reducing the radius, then the total amount of heat generated till that radius is going to be also going to reduce, because the total volume you are accounting is less, but psi v is constant. Psi v is not varying along the radial direction, that is constant. Is it clear? Do you have any tutorial after this? Hello?
No, sir.
Okay. So, is there any more question? Hello?
No, sir.
So, can we stop here unless you all are okay? Can we stop?